that we have like 2 hours left of lecture this semester. Do you feel good? Like one less class to think about? Probably not today. But if you have any homework questions, email me. You'll get there. Hang in there. So, almost there. Don't freak out too much about homework, please. It'll be okay. How does it feel to have one like after Monday, it's pretty much done. I thought about giving you like an extra one too. I was like, oh, they want more, but then and everybody, I could see the look on all of your faces. It's like, no, we're good, thanks. Are any of you disappointed you didn't get an extra homework? Let me ask that. Okay, were the homeworks challenging? Too challenging? Last one was pretty hard, yeah. First one was really hard when you get used to R. In between, were they? I don't know. I'm trying to get a feel for it. I really don't want to make people too anxious in this class. I just want to be on. It's hard to tailor it because each class is, has a different set of cohort of people and a different set of expectations. So, anyway, sorry. Thanks for the feedback. I really do want to make this better. Simultaneous to the same thing where it's like, well, I want to make this better, but I'm also pretty tired. I'm tired of the homework system. I got to tell you, it's got to be fixed up before the next class. Okay, so we have this first Bayes approach where I just picked a couple priors and I tried to justify it based on previous research. Let's see what happens. Here's what happens mathematically. Blah, 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 blah. What we're looking for in Bayes is the posterior distribution. So what we really wanted to describe is the distribution of beta 0 and sigma squared error once we have conditional on the data we've observed. This is how we notate that posterior distribution. And this is really trying to emphasize the point that in Bayes, every parameter has a distribution itself. Right? In the frequentist world, or I'm sorry, I don't want to use that term, but in the ML world that we were in before, we didn't say this. We weren't after the posterior distribution of beta 0. We just sort of assumed beta 0 had a distribution that was normal because of the way that large sample theory works. But now we're actually going to try to construct this posterior distribution for beta 0 and sigma squared. And what we're going to get from it is literally a distribution. Like it's going to be this range of values that beta 0 could be and a range of values that sigma squared error could be. How we construct that distribution is very similar to the way we did Bayes' theorem in the original, that little token example we see in the introductory statistics world from Thomas Bayes with disease, prevalence, and sensitivity, specificity of certain diagnostic tests. But here we basically say, this posterior distribution is equal to the likelihood of the data given the parameters. This is your model. That part right there I've highlighted, that's your model. That's the likelihood function that builds the ML result. That's where Bayes and ML have their shared tie. Right, so everything that's true about ML in the limit is true about Bayes because it's there too. The difference is the augmentation of the prior. This is the prior distribution for both of those parameters. And because I specified my prior so that we said something about beta 0 and then we said something about sigma squared, this prior distribution, when they're both together like that, we call that a joint distribution, like a multivariate normal. But when they're independent, when there's zero correlation between the two, we could separate them into being something to do with beta 0 and something to do with sigma squared. So that's where this gets phrased. And more often than not, if you're reading about Bayes, all this math gets rearranged, and basically you see this brand new character that shows up there that is specified, or the way you read this, you're saying that the posterior distribution right here, you read this thing, it looks kind of like a claw or a caliper or something that's old-fashioned. That said is proportional to is what that means. Is proportional to the model likelihood times the likelihood of the prior. Right? So it's always posterior is proportional to likelihood of the data, we usually call this first term, and likelihood of the prior. Oh, so there we go. So we can also do all of this. This is our posterior distribution right here. This is a This is the same likelihood, again, we had I took this part of the math from when we were doing the multivariate normal and the normal distribution. It's our likelihood function. We plug in y, we plug in parameters, we get a height. That's how that works. Same way. Same thing that you learned before. Now for the prior distribution, in this case it's normal. Again, now the prior distribution tells us how likely any value of beta 0 is given the values of mean and variance we fixed for it. So now instead of like likelihood of data where we plugged in data and parameters and got a height, now we're just saying let's plug in some value of the intercept and see how likely that happens to be based on our prior belief. That's what that's doing, right? So it's adjusting it. So if we pick a value of beta 0 that's something like 500, right? This normal distribution is centered around 100, and we know 99% of it's plus or minus like 6 points above or below, 6.5 points above or below. So anything outside of that has a very little likelihood. So basically we're saying it's virtually impossible to find a beta 0 that's not in this 6-unit interval around 100. That's what this is saying. So it's sort of eliminating the possibilities of what beta 0 could be for us. Similarly for the variance is a uniform distribution. The uniform distribution takes the maximum minus the minimum and puts it as the denominator in a fraction. So every value is equally likely. Right here. So here are some more terms. You ready for the Bayesian Velocity? Again, now, if you're interested in this, there are courses on campus I would recommend. First is Billy Skorupski's EPSY 941. He does a great job with this. You'll become better Bayesians by taking it if you're interested in it. Frown? No?
You're teaching.
I'm not totally teaching that class. Now, I'm teaching a class next semester, EPSY 980, that's Bayesian psychometric models. So if you're doing factor analysis or item response theory or whatever, and you're doing it with Bayes, that's the class that I teach. You're welcome to be in there. I will be less of a dyed-in-the-wool Bayesian. I don't think Billy's dyed-in-the-wool, but you know, less of a philosophical Bayesian than Billy is, because that's just, I'm not on that. We could just recognize there's a difference between the two of us. It's not for better or for worse. It's just what it is. But I'm more of the pragmatic approach to why would we use it, what do we get out of it. That's what we're going to do. So we'll focus less on Bayes, and we'll focus more on like factor analysis or structural equation modeling or IRT. And the way I'm trying to build it is, if all you knew was Bayes, what would each of these methods look like in implementation? Right? So the way I taught last year's SEM class, it was, if all you knew was ML, how would these look like in implementation? So sort of the analog to it. So more terminology. Again, don't worry, don't get too caught up in this, but that is one of the sticky points. So my spouse is an accomplished scientist and world-renowned for her work in multi-level, among other things, right? And she sits there and goes, I need a glossary when you talk about, or a dictionary when you start talking about Bayes, because all the terms. So if you're having a hard time keeping track of these terms, you're not the only one. People who are really good at what they do in their craft and not doing Bayes struggle with them as well. But let's try to walk through them. Bless you. Each of the parameters of the model for the data get prior distributions. So in our case, there was an intercept and a random or error variant, residual variance that we gave priors to. Those prior distributions have parameters too. Right? The uniform has two, an upper and a lower point, for instance. The parameters of the prior distributions, I kid you not, are called hyperparameters. I see glares. I didn't name it, man. This is not my naming convention. So the hyperparameters are the parameters of the prior distributions, whereas the parameters are what's in your model that you care about. Does that make sense a little bit? So the lower bound of 200 and the upper bound of 400, those are the two parameters of a uniform. Those are hyperparameters. And similarly, in the normal distribution that we picked as a prior, the mean of 100 and the variance of 2.13 squared is a hyperparameter. Oh, those are both also hyperparameters themselves. There are cases where you can have a prior distribution with parameters specified that you have not fixed to certain values, but you have estimated them. Often this shows up in a multi-level model, or one of the models that I will cover next year in EPSY 980. That is a case where, in a factor analysis, each person gets a factor score, a latent variable that we assume is related to the construct we're measuring with an instrument. We say that typically we say the assumption about the factor score is it's normally distributed. We often set its mean to 0, so that mean of it is a hyperprior, mean is 0, but we can go and estimate the variance of this thing. And when that happens, when we're estimating the hyperparameters, we call that an empirical prior. Yet another term. Empirical meaning, I really didn't pick it, the data picked that one, right? So there you go. Yeah. How we doing? Enjoying this? Nah, not so much. All right, let's talk a little bit about estimation. So Markov Chain Monte Carlo is commonly thought of as the only method for Bayesian estimation. And it's the predominant one. That's what JAGS does. There's other packages out there that do the same thing as JAGS. One's called BUGS, Bayesian Updating through Gibbs Sampling. One is called STAN. The M+ program has Bayes involved in it now, and there's a bunch of people, standalone stuff like my own, that do Bayes in smaller use cases than each of those. But there are other ways of estimating Bayesian models without having to use Markov Chain Monte Carlo. In fact, you remember maximum likelihood? The concept of maximum likelihood is we form this likelihood function. It's a function of the parameters, and we search that function for the peak, at the maximum. We can do the same thing with the Bayes analysis as well. Instead of a likelihood function, now we call this a kind of a posterior likelihood, right? We have the likelihood function multiplied by the posterior now, but we can still search it for a peak. And this often gets called something that's a little bit different. Because there's these deep-rooted philosophical differences that again, personally, I don't think are that big of a deal between Bayesians and people who don't do Bayesian. Maximum likelihood is not what we call that anymore. We call it maximum a posteriori estimation. MAP, maximum a posteriori. So it's a completely different way of saying it, but it means the same thing. You're finding the peak of a distribution. It's not just the likelihood of your data given the parameters, it also involves the prior distributions as well. That's it. That's all there is to it. So we could find that, and that's what I'm going to do first for you here. So we're going to do a grid search. I used Excel to search values of the data for when the variance is equal to the value it's supposed to give us of 239.490. I literally just plugged in values for the mean, and I did a search for it. And here's what we find. This is the likelihood function from ML with no prior. The maximum point is 102.8. Right? When we add the Bayes, the prior for beta 0 with a mean of 100 and a variance of 2.13 squared, that's normal. We shift the maximum from 102.8 over here to 101.4. What's the prior doing? Right? So now look at this. With no prior, we say mean 102.8. With a prior, with no data, the prior mean is 100. Right? So the result, when we combine prior and empirical evidence from the data likelihood, is somewhere in between, 101.4. You kind of probably could guess that, right? How are we doing? Seem weird? You also see that one of the things that's important in likelihood statistics is how curved the likelihood happens to be, because the curvature of this likelihood refers to how much variability there is in the estimate. You'll note, the more curved there is, the less the standard error happens to be around the estimate. So if you wanted to say, apply that same logic, again, it's a little bit fuzzy. It's not exactly what we do in Bayes, but I'm just going to kind of give you a comparison. The blue line here is more curved than the orange line. You can see that with the eyes. We could probably calculate that with the second derivative evaluated at the peak. We don't want to do that, though. what that means is the prior is telling you we have more information about where the mean happens to be than we would have had if we had just the data by itself. And that makes sense, right? Because the prior is functioning like another source of information. It's more informative analysis. So our standard error around the mean, around this estimate, will be smaller in this case in the Bayes analysis because of the influence of the prior itself. How does that make you feel? Is this dangerous? You could totally hack this, right? You can see where this could be misleading. What if my prior variance was 0 or 0.0001, right? We're going to have very little error around where that mean happens to be. So here's what I'm doing. I'm playing around with numbers now. Let's take that same prior mean of 100, but now the variance, instead of being 2.13 squared, it's 1,000 squared. Right? That is a really, what we call a really uninformative prior. It does not put much influence on the data. And what you'll see is these lines are practically parallel. The peak for both happens at 102.8, right there. They're at different heights, and that's because the addition of the prior adds that difference between the two. The data likelihood is the same for both. The only difference is the likelihood of the prior. But they're the same curvature as well. And this is where I'm going with the agnostic approach. You can still do Bayes, and you can say, hey, my prior, not that informative. I'm not putting that much weight of information on the prior. I'm just doing this to enable the Bayes estimation to go forth. Right, so I find this to be, if you're looking at a result in a paper where someone's using Bayes, and you're worried about the influence of prior choices they've made about priors on the distribution or the results they have, the first question you have is, what are the priors? And I usually ask, why did you pick those priors? And if you're a student in my program and you're doing some type of analysis for your PhD and you said because so-and-so did it in their paper in 2006 with the same prior, well, why did they pick that prior, right? You have to have, to me, it's a rationale for using it is almost everything because it's very subjective. It's a very subjective choice. You can pick anything for a prior. You want to see the opposite? Look at that prior. I say the prior is a mean of 100 and the variance is now 0.15 squared. So again, the orange line is the maximum likelihood estimate. The blue line's peak is right at the prior mean of 100. So how do you like that? So now your question would be, are you sure? Why did you pick a variance of 0.15 squared? That doesn't seem to make much sense. Right? Or maybe that has a lot of empirical support. I don't know. What do you think? This is how you can get past your PhD quick. I'm just kidding. I'm just kidding. This is why it's controversial. But you can see the controversy, right? You can see where the controversy is lying because the choice of prior may impact your result depending on how much data you have. If you have hundreds of millions of cases of data, the choice of prior isn't going to be that informative. Here we have 50 observations. It's pretty informative, what we do. Here's another approach. Instead of going normal, you could have said, hey, I have a uniform distribution for my prior. A uniform distribution it says every value of beta 0 is equally likely between negative 1,000 and positive 1,000. Now, I will argue with you about the uniform saying, why did you pick 1,000? Plus or minus 1,000 for the limits. Why not plus or minus 300 million? I mean, like, I've run models before the intercept or the mean it depends on the scale of the data, right? Here, a justification might be, well, it's the units of IQ, the way we typically measure it, have a mean around 100. Okay, makes sense. But you can see with a uniform prior, when every value of beta 0 is equally likely, this is also what we call uninformative because the peak of the prior likelihood right here and the peak of the ML is right about the same. You get the same value for both. So what I'm trying to tell you is Bayes is cool. The thing that makes Bayes cool with priors is also the thing that makes Bayes very controversial. It's why people have really rejected it for many years. I mean, there in the statistics departments I used to be to know a little bit more, Georgia, Nebraska, and Illinois, where I've worked or went to school. There were stories passed on by the professors who've been there a while who would talk about the sort of the two different camps of Bayesians and non-Bayesians that existed back in the 1960s and 70s, and how much you basically get in fights over either, right? Because of this whole, and it's literally been that controversial. Like, I don't know about like physical fights, but given the way that some professors manage to conduct themselves, I wouldn't be surprised. So, myself included, I guess. Although I've thankfully gotten 0 physical altercations because of my work. Hooray! All right, so how are we doing? Summarizing so far, Bayes means that each of the parameters in the analysis have some type of prior distribution. You can estimate Bayesian models using what we call MAP estimation, maximum a posteriori. Finds the peak of the likelihood. Bayes modal is sometimes we call that too. It's very difficult to do. There are cases of priors. We call these some families of priors that make some estimation easier than others. I kid you not, they're called conjugate priors. A conjugate prior is a prior where the distribution of the prior matches the distribution of the posterior. Technically speaking, in the example I showed you here, the distribution of beta 0, prior being normal, and the distribution of the data would have led to a conjugate prior. And I could have done it a little bit easier than this, but I didn't, just for sake of didactic purposes. Priors can be informative, meaning they have a big impact on the results, or highly peaked distribution, or uninformative, which is very flat distribution for the prior. Right? Okay, how are we doing? You ready for an estimation by brute force? Yeah, Markov Chain Monte Carlo, here we go. The basics of MCMC. By the way, if you're in physics, if you're in chemistry, I think we call this Monte Carlo estimation. Engineering, maybe. So remember I talked about, back with ML, I sort of said, in least squares, I said there's like 3 ways that we estimate things in general, more or less. That sort of means there's probably more, but I'm not going to talk about them. We minimize something like in least squares. We maximize something like in maximum likelihood. And the third one was using simulation to sample from something. That third one right now is what we're going to do for Markov Chain Monte Carlo. So prior to this part, bad choice of words, before this in class, we would form a likelihood function. We would then try to find the peak of the likelihood, and at that peak, we'd use those parameters as estimates, and then we'd figure out, based on statistics, what the sampling distribution of them should be. What we're doing now is basically saying, forget about using statistics to find the sampling distribution. We're just going to find the distribution of those parameters directly. Markov Chain Monte Carlo is effectively doing that. It's like the Etch-a-Sketch. You remember the Etch-a-Sketch back in the days? Or better yet, no. Ever done, I was trying to think of being a kid. You put the paper over something and you put a crayon on it, was it etching or what, you know what I'm talking about? Right? That's MCMC. It's a really rough way of getting a picture of a distribution. And so depending on the method, there's all sorts of MCMC algorithms out there. Some are really what we call efficient, that meaning you don't have to use the crayon over a lot of the surface, you can just get the key points in. Some are really inefficient, meaning effectively you're drawing the whole thing out and you're only taking a part of it, right? And so we're just going to go over, rather than get into the details of each of these, I'm just going to go on the high level, what's going on with the sampling process. Does that sound cool? This blows my mind when I do this, by the way. All right, MCMC estimation works by taking samples from the posterior distributions of the data given the parameters right here. Actually, this is the other way around. Posterior distribution of the parameters given the data. Come on, Templin. I can't even edit it. That must have been a picture I put in there. Gosh. Anyway, we're going to take a sample of beta 0 and sigma squared. So we have to do this multiple times because every time we draw a pair of values randomly, that's just one snapshot of it. Right? So there are a bunch of methods out there I talked about, so I'm not going to get too big into it. One is called Gibbs sampling. which is really efficient. It's really efficient, I find, but it's very hard to do mathematically. So not all the cases out there use Gibbs sampling, because to do the Gibbs sampling, you have to have the exact form of the posterior that you know what it is. And most of the time, we don't know what that is. Right? It just takes a lot of mathematical derivation to do, and sometimes it's very easy. Well, it's never very easy to do it. Sometimes it's relatively easy compared to the times that it would be very hard to figure out overall. There's another series of algorithms, first started by Metropolis. By the way, the paper date for the Metropolis algorithm, 1950. Can you imagine doing this in 1950? You wouldn't have very many computers, or any, really. That's when that, and then Hastings augmented it in the early 1970s, right? So this has been around, you know, good 60, 70 years. Can you imagine that? That's pretty amazing to me. Anyway, this is a very inefficient algorithm. It's called a random walk, effectively. We take values just basically from a distribution at random, and we say we essentially propose them, or we accept them or reject them. Basically, we accept them if they are a little bit more likely probabilistically than the comparison one. And at the end of it, we have this long chain of values that we try to summarize. And then the newer versions, there's one called hybrid or Hamiltonian Monte Carlo. If you're into certain fields, love this program called STAN. Some of the more famous people in Bayes worked on that recently. It's a nice program. It's much more efficient. It's a nightmare to install unless you're running a Mac, so I didn't give that to you here. And it's also kind of a nightmare to code, but we'll get there. Okay, so we're doing Metropolis Hastings. You don't need to know about that. Blah, 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 blah. Here we go. Let's talk about JAGs. Let's go to Bayes. So what happens in R here, to use JAGs, if you see my example in R, we get into this estimation with Bayesian right here. And the way that we're going to use R, we're going to use R to output data and write syntax for the program JAGs. So R is going to be hijacked, or it's going to hijack JAGs, run it, and then when JAGs is done, R is going to read in all the output from JAGs and make it work. Now, it may be, I haven't gone under the hood of the program, it may be as simple as calling an API or something like that, so it's not actually outputting things to disk, but it's like that. R is not doing, R is essentially being our shell program for using JAGs. How many of you have installed JAGs when I pointed the link to you? So a couple of you can follow along. If you haven't, totally cool, understand. In JAGs, we have to give everything the distribution. So I'm not going to go thoroughly into the code. If you want to learn more, take Billy's class or take mine later on. But here's essentially how it goes. We have our data. In my data set, we have Y has the data, the IQ scores I talked about. So here I say Y for a person, right? We have to loop over all the people. Each person's Y, and this syntax, this tilde is distributed as, and the D norm means normal distribution with some mean mu. And here's the part that drives me nuts about JAGs. You'd think tau would be a variance, right? But in JAGs, tau is actually 1 over the variance. Yeah, there we go. So this is why we have entire courses dedicated to this. But now that is the likelihood. This right here is the likelihood of the data given the parameters, right? Next, we need the prior likelihood. For mu, we can go and specify d norm. This is a normal distribution for likelihood. Mean of 100, variance of 1 over 2.13 squared. And again, I have to specify the variance as 1 over the variance because of the way JAGs works with this function. Similarly, I can use tau, the uniform distribution. The limits of it were between 200 and 400, but again, it's 1 over. So I had to go switch the limits and take 1 over both of those to make it work. But I'm going to save sigma squared as 1 over the tau parameter when we get this done. So we'll actually see the variance estimated. So in R, there's a package called R2JAGs. R2JAGs, this thing right here, which you can download and install. If we embed all this in a function argument, It's kind of like in Lavon where we put all the model in quotes. Now we're putting all the model in a function. We run this function. We specify the data and the things need for it. The parameters we're estimating, and we call JAGS. I use the JAGS.parallel function. What this is doing is creating what's called a Markov chain. So what we do in a Markov chain is the following. There are two parameters we're interested in here, sigma squared and mu. Tau is just a conduit to sigma squared. But what JAGS is going to do is it's going to randomly pick a tau and a mu to start with, just random values. And then for each step of the chain, it's going to suggest a brand new mu. Use a little math that I didn't show you on the slides. I skipped over that. To figure out you want is the new mu more likely or is the old mu more likely? Basically forms a probability. It takes, with a certain probability, it switches from the old one to the new one. Same thing with sigma squared. You got the old sigma squared, proposes a new one, compares the two, and with a given probability, it switches to the new one. And every time you, at the end of the chain, the one that you've retained, you keep track of. And so every time we call it an iteration in this algorithm, we sample both parameters and we keep track of them across a number of iterations. And that set of values that we have at the end of those iterations is called a Markov chain. And that is supposed to be our posterior distribution. That is the distribution of the parameter itself. So I'm just going to kind of run this real quick, see how long this takes. Only two parameters, took a little bit of time. But this is what we end up getting. Oh, please. I know figure margins too wide, yes. Yeah, no kidding. You know what? I have it in my slides. So here, this is the data set in R afterwards. There's mu, just take a look at the, don't worry about the deviance of the tau columns, mu and sigma squared. But this is telling us for every iteration of the chain that we've kept, what the value of mu and the value of sigma squared should be. Right, those are samples from that, the posterior distribution for both of these. Then, if we tabulate across that, we can come up with, so this right here, I actually ran two chains, two sequences of these. One is plotted in black on this plot, and one is plotted in red over here. They're overlaid right on top of each other. So you can see this, sort of this random walk behavior, right? It sort of looks like a seismograph going crazy. These are the values that it's proposing or accepting of each of the parameters as it goes through the likelihood. These are the iterations. I actually ran this chain 50,000 iterations, and I kept the last 10,000 for each, which is kind of excessive. But then if I were just take all those values and forget about which iteration number they were in, but just to plot them all together into a big distribution, this is what I'd find. This is what the density of mu. This is the posterior distribution of beta 0 right there. And so again, if we wanted to summarize this, the summary of this will tell us what the mean or what our parameter happens to be. Take a look at this crazy density of sigma squared. The thing kind of looks like a whale or, I don't know, maybe a wave. But remember, the prior distribution for sigma squared ranged between 200 and 400, right? And so there's a big chunk of this that's just butting right up into the lower bound. You can see it right down here where it needs to be. So now that's what Bayes gives you, or the Markov chain MCMC algorithm gives you. For each parameter, it's your etch-a-sketch distribution. That's what this line right here looks like. That's sketched in from each of those jumps around the algorithm is doing. How do you summarize that? What's your point estimate of the mean? What's the point estimate of beta 0 on this? Multiple ways of summarizing it. It's a distribution. One way is the mean. Take the mean of it. That's called the expected a posteriori distribution, EAP. You may want to take the mode or the median as well. But here, that's where I can switch back over to R and show you this. Right here. This tells us, for each parameter, the mean value, 101.32. That's the mean mu. Sigma squared, the mean value is 256.62. So these are the numbers you'd report, some of the numbers you may report in your study. Furthermore, if you wanted to tell, let's say this parameter, I mean, we don't really care about whether or not this parameter was different from 0. It's a mean. We don't really have expectations. But let's imagine this is a beta that you worried about whether it was different from 0. The way that you would tell whether 0 was part of it is to take a look at the distribution there and to try to figure out if 0 was contained in the bulk of that distribution. Right? You see, this distribution doesn't touch 0. So if we were going to do the sort of, Bayesians don't like to call it a hypothesis test, and it is a little bit different from our hypothesis test in the likelihood sense that we saw before. But here, we would see that 0 isn't contained in our interval around where the parameter is. So we'd say it's not likely that this parameter is 0. In fact, none of the values, the lowest value of this parameter was given in R here. Actually, it doesn't even give in here. The value at the 2.5 percentile is 98.28. Right? So the minimum is not very much further from that. So that gives you the value itself. Right? So we'd be able to say, hey, 0 is not very likely, or however you want to talk about it. What do you think of this? Weird? Too much information. Actually, the cool thing about Bayes is it tells you when you're wrong always. But this is sort of the density for each of these. These are the Markov chain, the posterior distributions. Flip through here. I didn't go too much into this, but the Markov chain itself, and if I see if I can show this to you. Hang on a second. I need to get a plot to fit in R, and then I'll mess with the plot axes. I'm going to do something that you can't see. But I'm going to run a chain that has like 500 iterations, and we're going to have no burn-in. What do we call that? So basically, I'm going to start from the beginning. I'm going to record all the values. There we go. This is what we have right here. Oh, dang it, R. No. Hang on a second here. Let me save it. It's coming, I promise. Desktop. Save. Okay. Everybody's whispering. God, this class sucks. I get it. Hang on. This is what I wanted to show you. All right, so this is a chain of 500 iterations, starting at iteration 0 here. And take a look at what we have. This is a little bit weirder shape, although actually this burns in pretty quick. We have here. So basically, what we end up doing in a lot of these is the more complicated the algorithm gets, the starting point for the algorithm is not very good. And it takes a while for the search, kind of this etch-a-sketch, to get to the middle part of the distribution. Sometimes we call this, so what we want to do is take that chain and lop off the first part of it. We call that a burn-in period. Oh, fun times. Sometimes we may want to, depending on whether we have a good or bad algorithm, sometimes we may want to not take every successive iteration, although that's not really that big of a deal if you summarize at the end. But how do you figure out all these? It's trial and error. And here's some annals of terrible chains. For instance, you want to have, sometimes these are called caterpillar plots or time series plots. Right, so this is the iteration number on the bottom, and this is the parameter value for each. You see this beginning, this part right here, the perfect one's on the top left. The one on the top right, this took a little bit of time to get down to kind of the central part of the distribution, and then it starts to look like more of a caterpillar. We'd want to chop off the first part of that distribution and then just take this last part. Now, you're probably saying, can you do that? Is that valid? Right? Well, yes and no. It's I know, look at that. I like it. If you think of it this way, what we're doing is taking samples from this distribution, then absolutely you can cut off any part of it, because if you were to restart the sampling process in the middle of this distribution, it would just bounce around from side to side. this part that we're at the beginning, we don't know where the middle part of the distribution is until later on in the algorithm. The cool thing about the Bayes algorithms from a math point of view is given a long enough chain, they should all converge. The terrible thing about that means is it depends on what long enough means for each of your data and model. So this is a case where we have a long burn-in. Actually, this is not too long. There's only 250 or so observations. Get much worse than this, let me tell you. This one down here on the bottom left, this is a chain that is doesn't bounce around very much. If you compare the bottom left with the top left, the parameter on the top left is jumping a lot more from iteration to iteration, where this one it's sort of staying at the same value. You don't see as much bounce around. It's what we call an autocorrelation. Often it means that you're not allowing the parameter a big enough range to move in the algorithm. That happens too. And then this thing at the bottom, that thing looks terrible. That is a chain that never found the central part of the distribution and has a high autocorrelation, right? So these are things that can go wrong, and it can be maddening if you're just new to Bayes to get this figured out. But when you get it work, basically when you run this algorithm, you have to check whether it's converged. One way of checking is to run multiple chains and effectively do an ANOVA, the within chain variance versus the between chain variance. Not exactly that, but a similar version of that. And that's what actually shows up in R right in my output. Oops. Right here. At the end of my output, it has this thing called R hat. R hat, you want to be around 1. If it's around 1, you have quantitative evidence to suggest the between chain variance is roughly equal to within chain variance, and therefore the chains have not only converged, but they're converged at the same spot. That happens very rarely. Actually, that's not the case. It depends on the type of model. Doing this in linear regression almost always works. It works really quickly. But then again, so does ML. So there you have it. Now we can change the prior, and I did that. I'll just show you my results in my slide. If I did a uniform prior again, like I showed you before, my mean gets more like what the ML version should be. And there's my chains. Cha-cha. All right, so now this sigma squared, I changed the prior, instead of being between 200 and 400, I allowed it to go from 0 to 50,000. And now you've got a little bit better shape to it. Although this distribution sort of looks kind of weird, huh? There's a little spike in it in one spot, and it's not exactly smooth. It's the Etch-a-Sketch, right? It's trying to do. So have I made you sufficiently skeptical of Bayes? I was going to have you do this for a homework, and I thought, I'm never going to get the homework system to work on this. Ryan, are you all right? No, we're done. So there we go. Here's an informative prior also, if I wanted to mess around, but you can see what works. Here's an example of a chain plot with an informative prior and so forth. So if you wanted to go and do the last part of my slides, if you want to do this in a little bit more complicated, what you're seeing now are people who are trying to enable you to do Bayes with some of the packages in R that you want without having to write all that code that I told you how to show. The bottom of my slides, if you run this, it'll take it a long time just to install, but I installed the Blavon package. And here is where I have some, yeah, of course, the plots don't show. I have the estimates. I can't even show you this. Just run my script. It does the path analysis the way you wanted it to do, and it shows you values. So, okay. I've just made a great advertisement for my course. But if you want to do, so here's the cool thing that I like about Bayes. Again, if you've got small samples, I like Bayes a lot better than some of the statistics we use because we don't have to rely on the assumption of large sample sizes to make them work. But yes, Bayes, to learn Bayes, it's one class won't do you enough. This was more trying to get you to understand what's going on a little bit and then moving from there. So we're almost on another break. What this means is if you haven't finished homework, the last hour of class can be used for that. Does that sound cool to you? Okay, so I'm going to stop. Let's take a 10-minute break. Those of you who are done with homework, I'll see you later. It's been great having you. Fill out your surveys. Those of you who want homework help, now's your time. Thanks, everybody.